Imagine you're halfway to school when you realize your phone is still on your nightstand. You stop, pivot, and walk back to your door. Your fitness tracker logs the effort, recording a 2-kilometer walk and a successful morning workout. You feel the physical fatigue of those 2,000 meters in your legs, but the tracker is focusing on a scalar value, distance, which misses the underlying physical result. In physics, we prioritize a vector measurement called displacement. Distance is the total ground covered, accumulating with every step. Displacement measures the straight line change in position, requiring length and specific direction. Because you return to where you started, your displacement is 0. Mathematically, it's as if you never moved. While our senses track distance as a proxy for effort, the physical world operates on displacement. Without accounting for direction, the numbers on your wrist provide a very limited view of your actual change in position. Highway patrol officers monitor vehicle velocity, a measurement that carries far more information than the simple speed reading on your dashboard. Your speedometer shows a scalar value, your instantaneous speed, but it lacks the context of where that energy is actually headed. Velocity is the product of that speed and the specific direction dictated by your steering wheel. This distinction changes how we define acceleration. In physics, acceleration is any change in velocity over time, not just the act of going faster. Since velocity includes direction, pressing the gas, slamming the brakes, or turning the wheel are all forms of acceleration because they alter your velocity vector. Every time you navigate a curve, you are accelerating just as surely as if you had floored the engine. The steering wheel acts as an accelerator by constantly redefining your path. Consider a car cruising at a steady pace until the driver spots an obstacle and hits the brakes. We can plot this sequence on a velocity time graph to see the math behind the emergency stop. The flat horizontal line tracks the initial constant velocity of the car during those first few moments of cruising. The downward slope marks the period of constant negative acceleration as the brakes work to reduce that velocity to 0. In this coordinate system, the geometric area underneath the plotted line is equal to the physical stopping distance. Multiplying the vertical axis, velocity in meters per second, by the horizontal axis, time in seconds, causes the time units to cancel out. The result is a pure measurement in meters, your total displacement. By calculating the area of the rectangle representing your reaction time and the triangle representing the braking period, you arrive at the core kinematic equations used in every physics classroom. These formulas define the exact physical margin between a safe stop and a collision, mapping the space required to shed momentum. We can push this logic even further by looking at objects moving in a perfect circle, also known as uniform circular motion. If you swing a set of keys at a steady speed, you might assume there is no acceleration because the speed never changes. But remember, the definition of a velocity vector. To remain constant, both the speed and the direction must stay the same. As an object moves in a circle, its direction shifts every fraction of a second. Its velocity is in constant flux. Because the velocity vector is constantly changing angle, the object is in continuous acceleration, pointing directly toward the center of the circle. Every move we make follows this rigorous logic. A dropped phone, a sudden brake, and a sharp turn are all just variables moving through a series of constant, predictable equations.